Alright, so this is part 2 of how to solve balanced force problems. This time we'll be doing problems with trigonometry, and these are most likely some of the harder problems that you'll encounter over the course of the unit. So if you're skipping to this video, just an overview of what we talked about in the lab. We know that if the forces on a system are balanced, then we know that the system travels with a constant velocity. And vice versa, we've got that if a system travels with a constant velocity, then the forces acting on that system are balanced. And notice that staying at rest also counts as having a constant velocity. It's just that your velocity is 0. And again, what this means is that when solving problems, here's how this translates. If the problem says anything about an object or a system traveling with a constant velocity, that should immediately tell you that the vertical forces or the y direction forces are balanced. And when you draw your force diagram, that they should look appropriately. Likewise, in the forces in the horizontal or the x direction, those have to be balanced as well. So when you draw your force diagram, they need to kind of look like they're balanced as well. Setting up our equations, we can also say that the sum of the forces that point up have to be equal to the sum of the forces that point downwards, just so that they balance. And we've got the sum of the forces that point right for the horizontal direction have to be equal to the sum of the forces that point left. In addition, we are also going to be using our force of gravity equation, which is the strength of the Earth's gravitational field, 9.8 newtons per kilogram, times the object's mass. Now, I'm going to do 2 example problems. I'm going to assume that you already know how to do trigonometry. If you need a refresher, please go watch my video about vector addition and trigonometry. That gives you an overview of the math skills that you need in order to solve these problems. For the rest of the video, I will also be rounding to the whole number because the focus of this video is really just how to set up problems and solve them. So we're not really focused on getting exact solutions to the proper sig fig. We're just going to be doing just set up and solve. Okay, so for our first example, we've got a box is suspended from 2 ropes. Determine the force of tension in rope 1 if the mass of the box is 5 kilograms, and rope 2 makes a 20-degree angle with the vertical. Find the tension in both ropes. So first up, we're going to identify our system. In this case, it's the block that we're interested in. So let's draw a force diagram for it. We know that we've got a force of gravity that points downwards on the box by the Earth. We also have a force of tension that will point to the left, and that's due to rope 1. So I'll call this FT1 on box by rope 1. And we have to recall that each different rope has its own tension. So here we've got the tension applied by rope 2. I'll call this FT2 on box by rope 2. So how do you know when we have to do trigonometry for a problem? Typically when you have to use trigonometry, it's because there's a force that is acting diagonal to everything else. In this case, the one that we're talking about is FT2. Notice that FG and FT1, they both point and are aligned in either the X and Y axis. FT2 is that weird one that's kind of at an angle versus everything else. So what we're going to do is first draw the vector components that make up FT2. So we're going to break it down into a vertical component, which looks like that, and a horizontal component that looks like that. And we've got the angle that's given to us in the problem. This is 20 degrees. And we're going to call this one ft2y and this one ft2x. Now, once we do this, we kind of start to see what is equal to what. For example, if we know that this box is just hanging there and it's not doing much of anything, we know that the forces that act along the x direction have to balance out. So what that means is we're going to identify the forces that act in the x direction. In this case, this is ft1 and ft2x up here, and those have to be equal to each other. So our x equation goes something like this. ft1 is then equal to ft2x. And we've also got an equation for the y direction. And what that is fg is equal to ft2y. So fg, which is the force that points downward, has to be equal to ft2y so that everything balances out in the vertical direction. All right, so let's start to get some numbers involved in here. We've got the force of gravity is equal to 9.8 newtons per kilogram times the mass, which is 5 kilograms. And that's going to be equal to 49 newtons. All right, so I've got all these numbers pre-calculated. Feel free to check as you go along. So what that means is that ft2y then is also 49 newtons. So I'm going to write that up here. That's 49 newtons. All right, so let's pause for a moment to take a look at what we have here so far. One of the things the problem wants is the tension in ft2. So we're going to take a look at this triangle. Right now, what we have is an angle, and we have one side. So once you have one side and one angle of a right triangle, we can pretty much figure out everything else about the triangle. Now, if we have this 49 newtons, we have to recognize the fact that this is the adjacent side, so the side that's next to the angle. And for that, we will need cosine. So setting up our trig identity, we've got the adjacent, which is 49 newtons, over the hypotenuse, which is ft2, is equal to cosine 20. Moving things around a little bit, and you can check this by pausing the video on your own. My ft2 ends up being 52 newtons. So I can write in my force diagram 52 newtons right up here, and we've solved for part of the problem already. In order to finish the problem, what we need to do is take a look at our force diagram again and take a step back. We've got to take a look at what we need, which is ft1 right here. And we'll recall that we said that that was congruent to ft2x. So now the goal kind of is to become able to find ft2x. Now luckily we've got a lot of information of our triangle, and there are many ways to do this at this point. You could do the Pythagorean theorem if you like, or you can do trigonometry. I'm going to stick with trigonometry, and I'm going to use this side here to set up a equation that involves the tangent of 20. So for my equation, I've got tan 20, and that's equal to the opposite side to the angle, which is my ft2x. That's the thing we're interested in, and that's over the adjacent. That's the TOA, my opposite over adjacent. That's 49 newtons. Again, moving things around, we get 18 newtons here. So this is 18 newtons, And if Ft2x is 18 newtons, so is Ft1, 18 newtons. Okay, so there we go. Problem completely solved. And let's move on to the next one. All right, we're going with something a little bit harder for our second and final example. In this problem, you drag a loaded sled, which has a total mass of 20 kilograms across the snow with a rope. There's 200 newtons of tension in the rope, and the rope makes a 30-degree angle with the horizontal. So the sled moves to the right with a constant speed. All right, so we know right off the bat that forces are going to be balanced in the vertical and horizontal direction. I'm going to identify the system first as a sled, and I'm going to proceed to draw a force diagram next to it. Here's our system. Let's go with the things that we know so far. We know that the force of gravity points downwards. This is Fg on sled by the Earth. And we've also got this 200 Newton force that points here. And this is Ft on sled by rope. And we already know that's 200 newtons, so let's write that there. Now, since this sled is on a surface, we know that it's probably got a normal force acting on it. And I'm going to draw this like up here, perpendicular to the surface that it's on. So we've got the normal force on sled by the snow. And right now we currently have things that are unbalanced. And we know that the sled moves to the right with a constant speed. So opposing the motion, we've probably got a force of friction here. And we're going to go with kinetic friction since it is moving. Force of kinetic friction on the sled by the snow. Next thing we'll want to do is identify any diagonal vectors that need to be broken down into components. So we've got the tension, which is clearly diagonal. We're going to draw the x component. We'll call it Ftx. And we've also got the y component, which is Fty up here. And let's label the angle of 30, which goes down here. Now, taking a look at our force diagram and the fact that we know that the sled moves to the right with a constant speed, we can start writing some equations for the forces and how they're related to each other. We know that the horizontal forces must balance, so we take the left force, that's equal to the right force. So we've got the force of kinetic friction is equal to Ftx. And we've got something interesting going on here in the y direction. Now we've got, in the y direction, we've got three forces here. We've got the force of gravity, which points downwards, but we've got two forces that point upwards. So here we've got the normal force and Fty. So when we write our equation, we need to make sure that our equation reflects that. So let's do the forces that point upwards, which is Fn plus Fty. That's equal to the force of gravity, because we were doing the forces that point up have to be equal to the forces that point down. So now we start to see a plan for solving this problem. Let's start first by finding some more numbers. We've got the force of gravity, which is 9.8 newtons per kilogram, times the mass. So we've got 9.8 newtons per kilogram times 20 kilograms. This ends up being 196 newtons. Okay, so working with our triangle, let's take a look at our triangle. We know that we've got 200 newtons here. let's find ftx first. So ftx is going to be given to us by this function here. We've got ftx, which is the adjacent side to the 30, over 200 newtons, which is the hypotenuse. The thing that relates those two things is the cosine of 30. So ftx ends up being 188. Alright, so when we get that on my force diagram, 188 newtons. Referring to our equations, we know that these things are equal to each other. So that's 188 newtons. So if the problem wanted us to find friction, we know that that's 188 newtons. Working for the normal force, that's the one force that's not given to us. So let's try to find that. We've got, still working with this triangle, we are now interested in FTY. Now, we can solve this any way we like. I'm going to set up a sine equation. So here we've got FTY, which is the thing that we want, over 200 newtons. This time FTY is the opposite, so that's going to be equal to the sine of 30. Okay, and FTY ends up being 100 newtons. So I'll write that up here, 100 newtons. So the following thing is probably one of the more challenging things to understand this unit. We need to figure out what the normal force is. So the way this goes is something that points upwards when added to 100 is equal to 196. So blank plus 100 is equal to 196. And luckily we already set up our equation for this. Now moving to our equation, the y direction, let me repeat. Blank plus 100 is equal to 196 newtons. So that's how that goes. Solving for the normal force, let's subtract 100 from both sides, and we get the normal force is equal to 96 newtons. Okay, so let me get that on the force diagram. And that's it. So we've got a completely labeled force diagram with all the forces labeled with on-by notation and numbers, and we've completely analyzed this problem. So if there are any questions left, come ask me in class. Otherwise, I will see you later.